Hello, my name is Helena Brown and I'm the lead technician at the SPALL lab at the University of Leeds. My talk will cover the latest developments in sediment characterisation, how these techniques allow us to understand more about the types of sediment in our catchment, where they've come from, and how this can inform sediment monitoring and management. Sediment characterisation means using analytical lab-based techniques to find out, amongst others, the size and shape, minerality and percentage of organics present in each sample. Sources of sediment can then be identified by analysing this data and is used to inform where the sediment has come from, such as erosion of bedrock, input from farmland runoff, or onshore marine environments. We'll look into how the data can distinguish between inputs later on. Previously, a lot of grain sizing was done using laser diffraction, which assumes all of the particles are spherical and then output size as a percentage of sample volume. These instruments can also only measure a small amount of sample per run, so the data isn't as robust as newer methods. One example of the limitations is that if sediment is very angular and elongated, laser diffraction techniques can make it seem as if there are two different sizes of sediment present, as it measures the long and short size of the particles as separate sediment groups. As we now have optical systems, each individual grain in a sample is measured. These instruments use cameras to photograph the grains as they pass through the machine. Once photographed, the grain sizer can analyse the shape and size based upon the chosen parameters. With these new methods, we can now find grain size from 0.01 micron to 3 mm and grain shape analysis from 0.1 micron to 3 mm. For scale, there are 1,000 microns in 1 mm, which shows a huge range of sediment size that can now be analysed. By comparing the minerality of a sediment of the geological bedrock maps, you can surmise whether the sediment is from that area, or if it was eroded upstream and has been deposited in that site. The data from sediment characterisation can then be used to validate models for erosional zones, flood risk, and other hazards. If you are looking to implement natural flood management schemes, you can pinpoint where these sediment sources are, and by identifying if they're from farming or erosion, you can choose the most suitable method. After installation, you can also use the same sampling and analysis methods as a monitoring technique to quantify how effective each scheme has been. At SPALL, we have the facilities, instrumentation and expertise to complete sediment characterisation projects. We can collect suspended sediment and bedload samples from field sites for analysis and then interpret the results to find the sources of sediment. We have experience in working with NGOs, landowners, academics and government bodies. To ascertain the provenance of sediment in a water body, regions of interest are obtained from SciMap and from there sampling sites are chosen. SPALL staff work with all parties to ensure the most informative sampling locations and events are captured. As Janet mentioned, not all input types are on SciMap, and as rainfall is done as an average, some high flow events may be lost if just SciMap is used. By working with landowners and other organisations, we can get a true picture of the catchment and the best sampling locations and any high flow events which would otherwise have been missed. This reduces the number of samples required to gain an overview of the catchment while retaining the resolution of the results. Sample preparation is often overlooked. If samples are ineffectively prepared and split for further analysis, then incorrect conclusions can be formed. For example, if the lighter and smaller organic grains are taken from the top for size and shape analysis, and the heavier and more angular grains are left for organics analysis, then an incorrect picture of a low organic but highly rounded and small sediment input will be formed. SPALL has the ability to dry large volumes of samples for further analysis and has a safe and compliant disposal route. There is a sample splitter which can create up to 8 identical subsamples to ensure comparability between results. Sieves at Crumbie Phi intervals, which allow for a percentage of total weights in each interval to be obtained for the sediment sizes too large to go through the grain sizes. This technique lets you know how much of the sediment falls into the category of clay, sand, gravel or pebbles. High precision scales can ensure accuracy when recording subsets and also for calculating suspended sediment concentration. SPALL can collect suspended sediment loads and bed loads, and the analysis techniques and outputs are slightly different for each. For suspended loads, you can pre-process by dissolving the organics within the sample using hydrochloric acid. This will allow you to know what percentage of suspended sediment is organic, from soil, farm animals and wastewater treatments, and which is not, such as fine sediment from bedrock. The lab then has a range of equipment which will allow the analysis of pH, conductivity and dissolved oxygen content. This can be used to back out the amount of vegetation and other wildlife which would be supported in the area, and also to quantify the types of pollution input. For example, if there are low oxygen levels and a high pH, this would suggest that there is an organics input which has caused an algal bloom, reducing the oxygen levels in the water. We can also obtain the concentration of suspended sediment by weighing a container, the wet weight of the sediment and river water, and then the dry weight of just the sediment. This can also be used to identify where sediment sources are. We can find the grain size from 0.01 micron to 3 mm and the grain shape analysis from 0.1 micron to 3 mm. The instruments we have can calculate these parameters for each individual grain within a sample, so the data is really robust. Quite often N can be over 10 million grains for most samples. This graph is from a previous project and shows the change in pH, concentration and conductivity along a catchment. As you can see, there are clearly two peaks, which are sediment inputs of organic pollution. For bed load samples, pre-processing also allows for the removal of organics through dissolving with hydrochloric acid or loss in ignition, which burns off the organic fraction in a high temperature oven overnight. We can also dry the samples, which makes it easy to remove agglomerations, subsample and pass through the grain sizes. Finally, we can split the samples into up to 8 identical subsamples. This ensures that you can conduct different analysis techniques against each subsample, and the results can be comparable to give an overview of the river at that sampling point. For the analysis, we can compare grain size and shape, put these into Columbian fire scale categories from clay to cobbles using either grain size or outputs or sieves depending on the sample, and use Munsell soil charts which show the type of soil present. By collecting both size and shape data for sediment, we can locate and differentiate erosional zones and sediment sources. The analysis methods above can be conducted for each sample and collated into figures which show trends across a catchment. The graph is from the same sampling project as the previous slide, but this time shows the analysis of the bed load. The top graph shows the D10, which is a red line, the D50, the green line, and the D90, which is the blue line, for each sample, where half of the sample had the organics removed by loss and ignition after it had been dried, and the other half was just dried. This shows that there isn't very much organic material in the bedrock other than at the first sampling location, and also that the particle size increases downstream up to sample site 20 and then decreases. This makes sense as sampling sites 21 to 25 were much further downstream, and the catchment was much flatter and slower moving, which allowed for the deposition of smaller grains. The bottom graph shows the sphericity of the grains moving downstream. The grains start off very well rounded, which when combined with the knowledge that there is a high level of organics means that there is deposition of fine grain organic silts from field runoff. The grains then become more angular, with peaks that show erosional zones of larger and more angular particles, and then depositional zones where there are smaller and more well-rounded particles. We can then visualise trending across the sample area. Outputs can be annotated to explain where the sediment has come from, deposition conditions prior to sampling, and the existence of any pollution sources across a catchment. The trending can explore shifts in mean grain size, grain shape, and other analysis methods like pH and conductivity to discover pollution and sediment sources. For example, here Grace has annotated the location of her samples, the size, shape, and minerality of the samples at that location, and how this relates to its journey to that position and the conditions surrounding its deposition. When these techniques are combined, the data can be visualised to be informative and engaging to a wider range of stakeholders. They do not require any previous knowledge of sediment analysis or fieldwork to be fully understood. This data can be used to inform flood risk models, placement of natural flood management schemes, and monitor the effectiveness of schemes once established. Thank you for listening. I hope you enjoyed my talk, and if you have any questions, please let me know. If you'd like any further information about the sediment characterisation methods mentioned today, or information about pricing and availability, then please get in touch via the email address listed. We're also on Twitter. If you add us at SeaFluids UK, then you can see some of the projects undertaken by the Sorby Lab suite.